because there's a little bit of review that I want to do. So let's get this going. Screen share. Hopefully this will work easily. Okay, turn this up a little bit, turn this over a little bit. All right. Actually work on a little bit of lighting here. Yeah, let me wait a minute before I start. Okay, so I've got here, I'm going to review a couple of minutes. For those of you who weren't here last semester, sometimes I start a little early when I have review material. I don't cover any new material during this time, but sometimes it's useful to kind of get back up to speed to where we were, especially if it's in the middle of a long calculation or something. In any case, this is a summary of some of the stuff we were doing in Tuesday night's lecture with a hydrogen 2 molecule, H2 molecule. The H2, we did 2 molecules. We did the carbon 12, C2, and now we do H2. The main difference being that in the carbon 12 nucleus is a spin 0 boson, and in the course in the hydrogen molecule, the nucleus is a proton, which is spin 1/2, and therefore a fermion. In any case, the wave function for these diatomic molecules, you got a pretty good idea of what the wave functions look like. The wave function, which I'll call capital psi, is a product of a center of mass wave function, which is basically just a free particle solution for the center of mass, multiplied times the central force eigenfunction for the relative motion, multiplied times the spin wave function. The Hamiltonian in the very good approximation we're using doesn't depend on the spin. So the spin part can be anything you want. Any spin wave function would work to give you an energy eigenfunction. However, by organizing it in terms of singlet and triplet, and that's what this notation means, is S is either equal to 0 or 1, meaning singlet or triplet. By organizing the spin part in this way, we make the spin part have a definite exchange symmetry, plus or minus, depending on the value of the spin. In fact, down here is the numbers. Call it sigma S. Is the spin exchange symmetry. It's -1 for a singlet and +1 for a triplet. You get that just by looking at the Clebsch-Gordon coefficients for combining 1/2 times 1/2. In any case, be that as it may, this is a version of the energy eigenfunction, which makes it also an eigenstate of the exchange operator. As far as the energy is concerned, the energy consists of 2 parts. There's the kinetic energy of the center of mass, that's from the phi part. And then there's the E and L, which is the energy of the relative motion. It's the central force energy. The spin doesn't contribute to the energy, so it doesn't appear here. In fact, there's a rough but reasonably good gives reasonably good idea of the energy eigenvalues E sub n L. It's given by this formula here. It's a shift for the ground, the bottom of the well minus V naught, plus a harmonic oscillator for the vibrations in the bottom of the well, and then an angular part, which gives you the rotational dependence on the energy levels. Here's the L quantum number, and R0 is the equilibrium radius. Am I hearing a question about this? If there's a question, feel free to interrupt. All right, in any case, the way this is set up, this is also an eigenstate of the exchange operator. The exchange operator commutes to the Hamiltonian, so we know they possess simultaneous eigenstates. But the way that I set this up, especially with the spin part, makes it in fact come out so that they are simultaneous eigenstates. And in fact, the eigenvalue is -1 to the L, coming from the exchange symmetry of the central force part times sigma S coming from the spin part. And in view of the symmetrization postulate and the fact that the 2 protons are fermions, this product has to be equal to -1. So this is a way of saying that the orbital exchange symmetry times the spin exchange symmetry has to be -1. So these 2 have to be opposite each other. So therefore, we end up with a table. We can set up a table that describes the possible states of the hydrogen molecule, beginning with names singlet and triplet refer to the spin states. This is spin 0 and spin 1, of course, S0 and S1. The degeneracies are 1 and 3. That's where the name singlet and triplet come from, obviously. It's just a number of magnetic quantum numbers. sigma s is -1 +1 because of how they behave under exchange. Now, the corresponding angular momenta, the orbital angular momentum of the diatomic rotor has to be even when sigma s is -1, because that gives you an even spatial symmetry, and odd if the spin symmetry is +1. So this is the -1 to the L, which is the spatial symmetry. And this is done in a way so the product of the two is equal to -1. Lowercase e12 refers to the eigenvalue of the exchange operator, which by the symmetrization postulate is required to be -1. That's why we set it up this way. So this is all a straightforward way of working through this, the consequences of these quantum numbers and so on. I just mentioned that over at the right, I've got a new set of names, which I'll bring over so you can see it, which is para and ortho. The expression para here refers to a state which is spatially symmetric, which is what you see here with L equals even. And ortho refers to a state which is spatially antisymmetric, and you get that with L equals odd. In the H2 molecule, these are linked to the singlet and triplet, as you see from this table here. But for other systems, the linkage might be different. So the terminology actually means different things. This refers to spatial symmetry, and this, of course, refers to the eigenvalue of the spin. Okay, so this is a summary then of the possible states for the hydrogen H2 molecule. In contrast to what we had with a C2 carbon-12 molecule, one of the main differences is that in the case of the carbon-12, the L equals odd states simply do not exist. You have only L equals even states. Whereas in the case of the hydrogen molecule, and by the way, the hydrogen molecule is just ordinary hydrogen gas. Just go into chem lab and make a bottle of hydrogen gas. That's what we're talking about here. So for ordinary hydrogen gas of H2 molecules, both even and odd angular momentum states are allowed. So question is, does that mean that there's no physical consequences of the symmetrization postulate? And the answer is quite the contrary. There are important physical consequences, and they come about mainly because of the spin degeneracies that are associated with these orbital angular momentum states. In particular, the even L have a spin degeneracy of 1, and the odd L have a spin degeneracy of 3. So singlet and triplet, or para and ortho, are connected with different spin degeneracies. Now, this has an important this has an impact on the statistical mechanics of hydrogen gas. Let's examine this in two cases. Maybe I'll start with a new piece of paper here. Let's examine this in two cases. We'll have one which will be a high temperature case, and one will be a low temperature case. So let's have high temperature. We'll talk about that one first. And let's talk about the para states and the ortho state. No, let me do the table better. Let's do it this way. Let's have high temperature here. And then up here, I'll have a para states, and then I'll have ortho states like so. We'll make a table that looks like this: high T and low T. We'll do high T and low T, high temperature and low temperature. So at high temperature, and by high temperature, I mean high enough so that significant numbers of rotational states are excited. That would mean that the L quantum number you see here is, on average, is reasonably large. If that's the case, then the Boltzmann factor that gives you the probability of the various states for the different orbital angular momentum states, the factor is either minus beta E sub L, where E sub L is the orbital contribution to the energy. It's this business over here. It's really a rigid rotor energy contribution. So as L goes from L to L plus 1 to L plus 2 and so on and so on like this, it's obviously alternating between even and odd states. And as it does so, the degeneracy of the spin part switches between 3-1, 3-1, 3-1 like that as you move across. Now, if as I say, the L number is reasonably large, then the energy E sub L is almost the same for neighboring L states. The L plus 1 and L have almost the same energy. And so the Boltzmann factor for two neighboring states is about the same. It doesn't really distinguish between them in terms of the probability of the states. However, there's a degeneracy factor in here. It comes from the spin degeneracy, which, as I've explained, is either 3 or 1. So for the L equals even states, in which the degeneracy is 1, versus the L equals odd states where the degeneracy is 3, it implies that the L equals odd states are roughly 3 times more likely to be occupied at high temperature than are the L equals even states. So what this means is that at high temperatures, the L equals odd, which are the ortho states, occupy about approximately 75% of the hydrogen atoms, whereas the para states, which is L equals even, are about 25%. Now, on the other hand, at low temperature, if you go to low T, of course, the system wants to drop into the ground state. Well, the ground state is the L equals 0 state, which is even. So at sufficiently low temperature, everything goes into the ground state, and you have 100% of the system is in the para states and 0% are in ortho, like that. By the way, the para, just to remind you, is L equals even, and the ortho is L equals odd. Just fill that in. So we get this table like this. So people sometimes distinguish between two different, in effect, species of the hydrogen molecule H2, and they speak of orthohydrogen and parahydrogen. So at high temperatures, you have a 3-to-1 split between them, and at low temperatures, it all turns into parahydrogen. Okay. Now, this has an important impact on the statistical mechanics of the hydrogen molecule. In particular, if you look at the specific heat, you will find that the specific heat of the, due to the rotational degrees of freedom, you'll find the specific heat at low temperatures is significantly different than what it would be if you calculated it, ignoring the symmetrization postulate. You know, if you didn't know about it, you'd get the wrong answers by the significant amount. I mean, it would give you really wrong answers. So this is one of the physical manifestations of the symmetrization postulate. It's on the thermodynamic state of or the equation of state of the hydrogen molecule at low temperatures. Actually, the story of this is more interesting and rich than you might even think, based on what I've said, because there's a question of equilibration time. The issue is this: is that you can see that if I have hydrogen gas at high temperatures, which is the first row here, you have a 75-25 split. But you can see that as you lower the temperature down towards basically the boiling point of hydrogen, be enough to do it, most of these ortho states have to convert into para states. You have to get transitions to do that in order to bring it into the thermal equilibrium. So that's what's involved in equilibration as you lower the temperature. On the other hand, in order to make such a transition, it's necessary to flip the spin. It's got to go from a spin triplet to a spin singlet. The spins are the proton spins, and they are, the way to influence them is to put them in a magnetic field. Well, if you have a bottle of hydrogen gas, the molecules are bouncing into each other, and the only magnetic field that the protons see is basically from the protons of the other hydrogen atoms that are bouncing into it. And those magnetic fields are really weak. So it takes quite a few bounces in order to induce a spin flip. And the result is that the equilibration time is rather long. I think it's, I forget the numbers exactly, and maybe somebody in the audience knows, especially if you're in a chem department, you might know. But I think the equilibration time is measured in weeks or maybe even as much as a month for this to take place. So what that means is that if we take ordinary hydrogen gas at room temperature and lower it down on a shorter time scale, like let's say over an hour, you're going to get distribution of the ortho and para states, which is the same as it was at the high temperature. What will happen is that the translational degrees of freedom will equilibrate, and the temperature of that will go down, you know, to whatever 20 Kelvin, whatever you're driving at. But the temperature of the rotational states will not. In fact, it isn't even equilibrium anymore. The rotational states will not be in equilibrium. What you'll have is that you'll have 25% in L equals 0 and 75% in L equals 1, because it's easy to make transitions within the different classes, but not across them, because going across requires spin flips, you see. All right, so in any case, it's easy, therefore, to obtain low temperature hydrogen gas, which is not in equilibrium in its spin states. This process can be speeded up by the use of catalysts. So if you want it to happen quickly, you can do it. There's experimental ways of doing it. But in the absence of catalysts, it takes a long time. So as a result, it's possible to create these non-equilibrium situations at low temperatures. This is an example of a system where some degrees of freedom are in thermal equilibrium and others are not. In fact, what you're really getting here is a population inversion. something that never occurred to me before preparing tonight's lecture is that population inversion in principle could be set up as a energy pump for a laser, or in this case, it would be a maser. I have no idea whether it's possible to build a laser out of hydrogen gas that's been cooled in this manner. Somebody might know, probably not, but in any case, it's worthwhile noting that this is what you get when you do that. All right. Oh, and then by the way, if you wait for a month for the thing to equilibrate, or maybe faster if you've got a catalyst, as you make the transitions from the L=1 state to the L=0 state by making spin flips, the kinetic energy of rotations is going to be transferred into kinetic energy of translations. And the result is that the translational temperature, which is what would be measured by a thermometer, will increase. The gas will spontaneously warm up, as a result of that. All right, so there's all these interesting physical consequences that come from the symmetrization postulate in the case of the hydrogen molecule. Okay, that's all I want to say about the hydrogen molecule and my general introduction to identical particles. Are there any questions about that before we move on to another topic?
I had a quick question. You're talking about at the large T limit,
Yeah.
it'll spontaneously warm up.
The first row here, yeah.
Yeah. Or sorry, after you wait a very long time.
Yeah.
Yeah. How much warmer will something get? And will it continue to get warmer after a month or so, or?
Yeah, well, I mean, if you could keep it insulated so you could tell that the temperature increase, yeah, I mean, it would take place over the equilibration time. You'd find that it gets warmer as measured by what the thermometer is going to measure is the translational temperature, because it gets bonked by the thermometer bulb gets bonked by the molecules as they bounce off. So it's measuring the kinetic energy of the molecules, average kinetic energy.
Okay.
But as it equilibrates, the rotational energy that's contained in those states that are taking a long time to make the transition, that's going to be transferred into translational energy. You can see that if you have two molecules bouncing together and the rotational state decreases in the collision, it's delivered an impulse to the to both molecules, translational degrees of freedom.
Okay. Thanks.
By the way, just for fun, I don't know if anybody's noticed this, but I posted these videos of called, I think it's something called entertaining videos or something like that. And one of them is a model of this purely classical model of a gas of two different types of atoms, blue and red atoms. And they cool off. And as they cool, they first form a liquid and then they form a solid. And I wrote this video, my completely amateur effort on it. I created this video because I wanted to find one for my daughter who was studying, chemistry in high school, and I couldn't find one online. Anybody ever made one of these things? It should be obvious, People do classical simulations all the time. Why don't they create interesting videos and post them? Maybe they do now, but in those days I couldn't find. Anyway, take a look at the video. It's quite interesting to watch. You'll see these atoms form diatomic molecules. You'll see them vibrating and rotating. They bonk into each other. Sometimes they break apart. And as the temperature is lowered, it gradually turns into a liquid, and then it crystallizes as a solid when it gets cold enough. It's really very interesting. It's all classical simulation. All right, anyway. So that's enough for an introduction to identical particles and enough for the hydrogen molecule, carbon molecule too. And let's move on now to a new topic, which will be the subject of helium. Helium is, of course, a two-electron system. Electrons are identical fermions, so the symmetrization postulate plays a role in quite a big role in the structure of helium. Okay, so to begin with, let's talk about helium. Helium is, of course, got Z = 2, and it has two electrons, a nuclear charge of 2. We'd also like to talk about, in the same breath as helium, we'd like to talk about helium-like atoms. These are ones that have an arbitrary nuclear charge with 2 electrons. So for example, hydrogen, helium, lithium, lithium is the next one, right? So lithium plus is Z = 3. Beryllium plus plus is Z = 4. These are ions which have which have 2 electrons. So we speak, for example, of helium like beryllium. That's what the beryllium plus plus ion is. Helium like lithium and so on. These are helium like atoms. We might as well treat them all together because the formalism is almost the same. As long as we're talking about helium like atoms, there's an important case that I want to add to the table and not forget about. And that's the case of the H minus ion. So the H minus ion has got, let me draw some axes here. Let's draw some coordinates here, X, Y, and Z, to get a picture of our atom. We have a nucleus that has a charge of plus ZE. And then we've got 2 electrons that are sitting out here at some locations like this. And let's call this distance R1 and this distance R2. And let's call the distance between the 2 electrons R12, like this. Let's make that the geometry of the atom. So an ordinary helium Z is equal to 2. You got charge of 2 in the nucleus and 2 electrons. In H minus, the nucleus is a nucleus of a hydrogen atom. In other words, it has charge of only 1. It's 1 proton, in other words. Now, it's not obvious that 1 proton is able to bind down 2 electrons because electrons repel each other and there's more negative charge than there is positive charge. In fact, in other words, it's not clear that H minus even exists as a bound state. You can certainly take a box and throw 1 proton and 2 electrons into it, but whether it forms a bound state or not is a different story. The system exists. Does it have a bound state? In fact, it does, it turns out. There was a certain period in history in which that was not known because people hadn't done it experimentally yet, so it wasn't known whether H minus exists as a bound state. In order for the single proton to bind down 2 electrons, the electrons kind of have to stay, if I use my hands, they stay at opposite sides of the proton. It's obvious they want to stay away from one another. All right, in any case, H minus does exist. This is Z equals 1, and it's another example of a helium-like atom, a particularly interesting one. The second electron is rather weakly bound, as it turns out, and not surprisingly. H minus, by the way, is interesting in applications. It occurs in stellar atmospheres, and it's important in energy transport in stellar atmospheres. So it's a problem in astrophysics that arises. It's also used in proton accelerators, like in the LHC. They have to use low energy accelerators to fill up the main ring before they crank it up to higher energies. And they actually do this not with a proton with a plus charge, but they do with H minus with a minus charge. And then they pass the beam through a thin foil, which strips off the electron, and suddenly you've got a proton beam. That's how they do it. There's a reason for doing that, having to do with filling up phase volume and Liouville's theorem and so on. Accelerator people know about this and can tell you about it. All right, anyway, so these are helium-like atoms. Now the Hamiltonian we want to look at, and I should say, first of all, that let's use atomic units. There's no point not to, it saves a lot of writing. Atomic units are units in which E equals H bar equals M equals 1, as I hope you know by now. So the Hamiltonian in atomic units is the kinetic energy of electron 1, it's P1 squared over 2, plus the kinetic energy of electron 2 is P2 squared over 2, minus Z over R1 for the interaction of and Z over R2 for the interaction of the 2 electrons with the nucleus, and then plus 1 over R12 for the interaction of the 2 electrons with themselves. Let me box this here like this so we can view the Hamiltonian. In this Hamiltonian, I'm implicitly assuming that the frame has been attached to the nucleus as in this picture here. The nucleus is not really an inertial frame because it moves around, it accelerates around somewhat. But since it's so much heavier than the electrons, it doesn't accelerate very much. And it's a pretty good approximation to treat it as if it were an inertial frame. Of course, we could do something similar to that in hydrogen as well. And we know that if you want to do it right, you really need to have a 2-body problem and correct for the electron mass gets replaced by the reduced mass and so on. But these are small corrections, and I'm skipping them here in the case of helium. Those small corrections are called mass polarization terms, which you may recall you went through this in a homework problem last semester. In any case, numerically, it's a good approximation to use this Hamiltonian. I'm also ignoring fine structure effects, which I could say quite a bit about, but they're small, so let's leave them out. And the result is that we get a Hamiltonian, which is a purely electrostatic Hamiltonian, which numerically is quite good for describing the dynamics of helium. All right. Now, this is a purely electrostatic Hamiltonian, does not involve the spin. We know if we had fine structure, we would get spin, but those are small, so we'll leave them out. At that level of approximation, it's similar to the electrostatic model we had in hydrogen, which would have been p squared over 2, or hydrogen-like atoms, minus z over r. We know that in the case of the electrostatic model of hydrogen, that we can solve it. And if we do, we get pretty good results. In hydrogen in particular, we get energy levels that are within about 10 to the minus 4 accuracy of the correct energy levels. There's a splitting induced by fine structure and so on, but the gross structure is really quite good without ever worrying about spin at all. So now the question is, can we do that also in helium? Can we solve this as a purely orbital problem and get good energy levels? The answer is no, it doesn't work for helium in the same way. And the reason is that spin is much more important in the case of helium than it is for the gross structure of helium than it is in the case of hydrogen. And it's not because of spin-dependent terms in the Hamiltonian, which I'm neglecting here anyway. It's because of the requirements of the symmetrization postulate. That's the thing that does it, because we now have 2 electrons and we have to anti-symmetrize the wave function. So spin is much more important in helium at this level of description than it was at hydrogen and at an equivalent level of description. So to deal with the spin and its effects, I want to talk about Hilbert spaces and exchange operators. Let me take that as the next topic, as Hilbert spaces and exchange operators. Let's talk about a single particle. By here, I really mean an electron, just for practice first, before we do 2 particles. The Hilbert space for a single particle, of course, we know can be decomposed into a product of an orbital space times a spin space. We did this with hydrogen. As far as the basis states are concerned, the basis states in the orbital space are the position eigenkets, and for the spin part, there's the magnetic quantum numbers. We take the tensor product of these, and we may call this xm, like this, as the basis states for the total Hilbert space of a single particle system. That's simple enough. Now let's do the similar thing for 2 particles. In this case, the total Hilbert space is the orbital space for particle 1 times the spin space for particle 1. It's tedious to write this out, times the orbital space for particle 2 times the spin space for particle 2, product of 4 spaces like this. The parenthesized numbers here indicate are the labels of the particles. We can rearrange these factors and put the orbital factors together and the spin factors together and write this as E orbital times E spin, like this. This is not the same as what I have above. This is up above is for a single particle, and this one's for a double particle, 2 particles. In any case, let's do that. And in this case, what I mean by E orbital is I mean the product of the orbital spaces for the 2 particles, E1 times E2. And if I do this, then the basis here is x1 for particle 1 and x2 for particle 2. Tensor product, and this can be written as x1, x2, if you want to write it more briefly. And similarly for the spin, this can be written as E spin for particle 1 times E spin for particle 2. And again, we can have basis states which are M1 tensor product with M2, which is just M1, M2. But it's worthwhile noting that we can also form linear combinations of these and transform them into singlet and triplet states. And at some point, we'll want to think about doing that, because these are 2 different choices for the spin Hilbert space. But in any case, the total Hilbert space for the helium atom is a product of orbital times spin, where the orbital space basically consists of wave functions of 2 particles, x1, x2. And then the spin part is just these spin products like this, or singlet and triplet. All right. Now then, this means then that in the E equals E orbital times E spin, the basis states that we can get are x1, x2, tensor product with M1, M2. And we can write this as, again, by abbreviation, as just x1, x2, M1, M2. Let me do it that way. Now then, having done that, I want to define exchange operators. There is the overall exchange operator, which I actually defined in the last lecture. and it acts on X1, X2, M1, M2. This is the same formula, in fact, as we had in the case of the hydrogen molecule, and produces X2, X1, and M2, M1. It swaps both the spatial and the spin labels like so. However, it's also possible to define purely orbital exchange, where this is the same vector here. And what that does is it just swaps the x's, X2, X1, but it leaves the spin parts alone, M1, M2. Or we can define a purely spin exchange of the same states, which gives me X1, X2 for the x parts and M2, M1 for the spin parts. It's possible to define these three types of exchange operators. Now, the symmetrization postulate only involves overall exchange. Why in the world am I introducing these others? Why do I care about them? The reason is that the particular Hamiltonian that we are interested in right now, in fact, is a purely orbital operator. And so it commutes with orbital exchange. It commutes with total exchange as well, because the spin doesn't matter. But what the point I'm making now is it also commutes with orbital exchange. By the way, it commutes also with purely spin exchange because it doesn't depend on spin at all. In fact, it commutes with all spin operators, not just exchange operators. So this Hamiltonian commutes with both orbital and spin exchange separately. Now, it also happens to be a fact, as you can see by looking at these formulas, that the total exchange is the product of the orbital times the spin. If you just do one after the other, you will end up swapping both the x's and the m labels, and that gives you the total thing. All right, so we have the following situation is that our Hamiltonian commutes with E12 orbital, and our Hamiltonian commutes with E12 spin. And moreover, E12 orbital and E12 spin commute with each other. And how do I know that? Well, it's because they act on different degrees of freedom. But if you don't believe me, go back to these formulas here and just check it out. You'll see it's easy to show that they commute. And so the result is that for this particular Hamiltonian that we'd like to solve, we have three commuting observables. Two of them are symmetry operators, orbital and spin exchange, and the third one is a Hamiltonian. That means that they possess simultaneous eigenstates. Moreover, if we have a simultaneous eigenstates of E12 orbital and E12 spin, then it's automatically an eigenstate of E12. And that's important to us because the symmetrization postulate says that the eigenvalue of E12 has to be -1 because we have two identical fermions. So we can achieve that, you see, by finding eigenstates of H that are simultaneous eigenstates of orbital and spin exchange separately. This just should have been a spin here. Orbital and spin separately with opposite exchange symmetries, +1, -1, or -1, +1. All right. Now, so as often happens, or usually happens in the case of symmetry operators, so when we want to find the simultaneous that commute with a Hamiltonian, if we want to find the eigenstates of the Hamiltonian and the symmetry operators, it's usually easiest to start with the symmetry operators first because they're simple operators. So let's do this here. So for our problem, let's start by finding out an eigenstate of, let's say, E12 spin. How do we get E12 spin? Well, the way to find an eigenstate of E12 spin is to write the eigenfunction as an arbitrary orbital state, which I'll indicate by a lowercase psi, multiplied by a spin state, which I'll put into singlet and triplet form, which I do because this has a simple transformation law under spin exchange. In fact, what this will do is bring out this sigma s factor, which I introduced earlier, times the SMS. And to remind you, the sigma s factor is just the exchange symmetry of the singlet or triplet state. It's -1 for a singlet and it's +1 for a triplet. So this gives us the eigens, and the psi here is the spatial part of this wave function is anything. It's anything if all you want is an eigenstate of E12 spin. All right, so it looks like that. This is really just separation of variables if you want to make that happen. Now, to make it an eigenstate of E12 orbital, the E12 orbital only acts on psi. This lowercase psi, this ket here, represents an element of the Hilbert space E orbital. It's this. Here, let me bring it up here. It's this space E orbital up here. This E orbital space is just in wave function language is just the space of wave functions psi of x1, x2. That's all it is. And that's what this state. This is what this state psi down here in Ket language means. It's just a purely spatial wave function of two particles. So E12 orbital acting on a spatial wave function like this gives us an eigenvalue E12 orbital acting on psi. And this is either equal to plus or minus 1. What this means is that psi, the wave function of x1, x2, is either equal to plus or minus psi of x2, x1. Because that's what E12 orbital does, it just swaps the x1, x2 labels. So to summarize then so far, if we want a simultaneous eigenstate of both orbital and spin exchange, the way to do it is have a purely spatial wave function psi, which is either even or odd under exchange, multiplied by spin singlet or triplet states, which are also either even or odd under exchange, with odd being singlet and even being triplet. And then we choose this exchange symmetries in such a way that they're opposite one another, and that will automatically make it an eigenstate of E12. All right. Now, we also want, so that's how we set up eigenstates of E12 orbital and E12 spin that end up having the right total exchange symmetry required by symmetrization postulate. We also want them, of course, to be eigenstates of the Hamiltonian. If I apply the Hamiltonian to this thing, and I want E to come out, the same thing come out on the right-hand side, you can see that this is fundamentally really just a purely orbital problem, because the Hamiltonian operator is a purely orbital operator. So it really only acts on the orbital part. We might as well write it as just H psi equals E psi, reinterpreting H now as an operator on just the orbital Hilbert space and not the total one. I mean, it's a trivial operator in the spin anyway. Or to put it another way, put it in the wave function language, we write it this way as psi of x1, x2 is equal to energy E times psi of x1, x2. Now, this is the hard part of the problem, is to solve this equation, because the Hamiltonian operator is complicated. But what we've done so far is to take care of at least the symmetry part of it. Yes, question.
Yeah, just quick questions. I'm a bit confused because I thought that the exchange operator acting on like the tensor product Hilbert space of spin and orbital was effectively like a product between an exchange operator on the spin space and a exchange operator on the orbital space.
Yes.
And if that's true, and you have these two, like you've separated your wave function into a product of a state on one Hilbert space and a state on another one.
That's
and
right.
Yeah. And psi is an eigenket of the orbital space.
That's right.
Exchange function, and the other one is an eigenket of the other Hilbert space exchange function.
That's right.
Then how come you don't have any psi SMS like that being an eigenket of the combined Hilbert space exchange function? Do you understand my question?
I do, and the answer is it is. If all you want is the eigenstates of exchange operators, all you need to do is this psi can be any wave function that's just symmetric or antisymmetric under exchange, and the SMS is automatically symmetric or antisymmetric depending on the value of S. So if all you want to do is set the symmetry up right, then the psi could be almost anything. It has to be even or odd under exchange. Except for that, it could be almost anything. It doesn't have to be an energy eigenfunction. But that's just because so far I'm just looking up to the point I'm in this presentation that I'm pointing at with my finger right now. Up to that point, we were only looking at the symmetry operators. But now when I'm down here, what I'm saying is we also want to be an eigenstate of the Hamiltonian. So to do that, the spatial part has to be a spatial eigenfunction of this Hamiltonian operator, which is in fact a purely spatial operator. Did I answer your question?
I think so. So you're saying the condition that the spatial and spin like pieces of the wave function have opposite signs in their eigenvalues of exchange?
We do that if we want to satisfy the symmetrization postulate.
I see. Okay. Thank you.
Right. And we're using the fact that the total exchange is a product of these partial exchanges. So we find eigenstates of the two partial exchange, they commute with each other, so they possess eigenstates. So we find them. Those things are automatically eigenstates of total exchange.
Got it. Thank you.
Okay, all right. Now, this is the hard part. This is where we really need to deal with the nitty gritty of what this Hamiltonian looks like. But it's now a purely spatial problem, and the spin has disappeared. So this now gives us a program for finding solutions that satisfy the symmetrization postulate. We solve this equation as a purely spatial eigenvalue eigenvector problem. We symmetrize or anti-symmetrize the solution if necessary to make them eigenstates of orbital exchange. And then we multiply the result by a spin wave function, spin state, either singlet or triplet, with the opposite exchange symmetry to create a total wave function, including spin, that has the correct exchange symmetry as required by the symmetrization postulate. Now, really what I've done here is I've reproduced the rule, which I think you should have learned in your undergraduate course, which is that the energy levels of helium consist of a product of wave functions, a spatial part times a spin part, that have opposite exchange symmetry. That's the usual thing that people teach you. But what I want to point out about this is that this decomposition in this rule, which is a useful rule, is actually specific to this particular form of this Hamiltonian, this particular system. In particular, if I were to include spin orbit effects, then there would be spin-dependent terms in the Hamiltonian, and it would no longer commute with E12 orbital to E12 spin separately. So this method wouldn't work, and therefore including spin orbit effects, for example, the ground state of helium, let's say, including spin orbit effects, is not in fact a factorization, does not factor into a product of a spatial part times a spin part with opposite exchange symmetry. It does satisfy the symmetrization postulate. It is antisymmetric under total exchange, but it's more complicated than this situation I'm describing here. These operators E12 orbital, E12 spin are useful for this problem, but they don't have a fundamental significance like the total exchange E12 does. There's no symmetrization postulate for them. Okay, and their relevance is really only applies to Hamiltonians of this form. Now, there are a lot of cases in practice in which we ignore spin. The spin effects frequently are small and we throw them away. So for systems like that, which you want to take into account symmetrization, you can use this technique or generalizations of it to higher, larger numbers of particles. So that's okay. I just want to point out that this is not some fundamental thing we're doing here, but we're just exploiting the particular properties of this particular Hamiltonian. All right. All right. And okay. And so another thing that this has done so far then is to reduce the problem to the problem of analyzing just the spatial part. All right. Now, so that has to do with Hilbert spaces, exchange operators, and how we satisfy the symmetrization postulate here. All right. This gives rise to a table that I can set up. This is a table that's rather similar to what we had in the case of the hydrogen molecule. Let me run through it again. So let me begin with a name here, which is either going to be singlet or triplet. This is quite close to the table we had before, but not quite the same. Draw a line here. So singlet and triplet, the spin value is either 0 or 1. The spin degeneracy is therefore either 1 or 3, like this. And then I'll call it lowercase e12 spin. That's the eigenvalue of the spin exchange operator. That's -1 for the triplet, excuse me, -1 for the singlet and +1 for the triplet. This then requires that the exchange operator for the orbital part should be +1 and -1 opposite, that is to say, so the total exchange symmetry should be -1 as required by symmetrization. And if we do this and we end up with new names, which again, as in the hydrogen molecule, are para and ortho. And as in the hydrogen molecule, para means that the system is spatially symmetric and ortho means it's spatially antisymmetric. But because of the couplings of the quantum numbers, they're connected with singlet and triplet, as this table indicates here. And it's in fact the same coupling that we saw earlier in the hydrogen molecule. All right. Okay, so this then is an outline of the connections between the quantum numbers for helium eigenstates. All right. All right. Now, to go back to solving this problem, the H cycles E size is purely spatial problem. This is a difficult problem, and it's going to occupy us for more than tonight's lecture. And we can only do it approximately. When you've got a problem like this that's not exactly solvable, one thing you should do is to pay attention to the exact symmetries that the problem possesses. If it's not solvable, it doesn't have enough symmetries to be solvable, but it may have some symmetry, usually does have some symmetries that at least simplifies the analysis of the problem. So let me remind you, I'll write down the Hamiltonian again so we can look at it. Here it is. The kinetic energies of the two particles, the energy of interaction with the nuclei, and then the energy of interaction of the two electrons between themselves, one over R1, 2. Here's our Hamiltonian. Let me box it again. Let's look for various exact symmetries that this Hamiltonian possesses. An obvious one is rotations. This is a purely rotational, or excuse me, purely orbital or spatial operator, purely orbital operator here. And it's moreover a scalar. You can see that because the two kinetic energies are the square of the momentum p1 vector dot p1 vector, and so it's dot products of vectors. The distance between the origin r1 and r2 are also square roots of dot products of vectors, and the 1 over r1 2, that's the same thing as the magnitude of x1 minus x2 absolute value. And this can also be written in terms of dot products of vectors. It's the square root of the square of that vector x1 minus x2. And so this Hamiltonian commutes with rotations. The rotations in general are orbital rotations, which are generated by L, the orbital angular momentum, which is the sum of the orbital angular momentum of the two electrons. This Hamiltonian commutes with this L. Now, actually, P1 squared over 2, the kinetic energy of particle 1, commutes with L1. And P2 squared over 2 commutes with L2. In fact, both of these commute with both these operators. Same thing true for the potential energy interaction with the nucleus. The term that does not commute with the individual orbital angular momenta is the 1 over R1, 2. Because let's look at L1, for example. L1, as you know, is a generator of spatial rotations of particle 1. Look at this denominator. If we rotate particle 1, but not particle 2, then this distance between the two particles is not left invariant. It's not invariant. So this final term, 1 over R1, 2, does not commute with L1 alone, nor does it commute with L2 alone. The other 4 terms do. So it's this last term which destroys the symmetry under rotations of individual electrons. However, the last term does commute with total L, because if we rotate R1 and R2 separate, X1 and X2 separately by the same rotation, then the magnitude, of course, is invariant because magnitudes don't change under rotations. Notice here, by the way, that we have very easy ways of figuring out what commutators are 0 and which ones are non-zero without doing detailed calculations involving commutators, which would be a real pain in this problem to do that. If you just think of the angular momentum as generators of rotations, it makes it easy to see what commutators are 0 and which ones are non-zero. In any case, the point here is that H commutes with L, but it doesn't commute with the individual L1 and L2. Now, the 3 components of L, however, don't commute with each other. In order to have operators that do commute with each other, let's use L squared and LZ, the usual thing we do here. These are the 2 operators constructed out of the total L, which do commute with one another. And they also commute with H. So in effect, we're developing sets of commuting observables, which include the Hamiltonian. All right, what about the spin? This Hamiltonian actually commutes with any spin operator because it doesn't involve the spin at all. Interesting spin operators to use, however, are the total spin, which is S1 plus S2, and the Hamiltonian commutes with that. One reason that the total spin is interesting is because it commutes with exchange, the exchange operator. And as you'll recall, operators that commute with exchange operators are physical. So we want to work with physical operators, and that gives us a bias towards this total spin. And so then, as a next step, in order to get operators that actually commute with each other, as well as with the Hamiltonian, we look at this, the S squared and SZ, and so we'll add that to the list. And all 4 of these operators commute with each other. All right. By the way, there's also these three exchange operators, E12 orbital, E12 spin, and E12 total, which we can also add to the list. And we start to get a list here of operators that commute with the Hamiltonian and with each other. Finally, I might add parity, which commutes with the Hamiltonian. So these operators all commute with each other, and they all commute with the Hamiltonian, and they all commute with each other. The L's and S's commute because they act on different spaces. The exchange operators commute because in some cases they act in different spaces as well. And because the way we set it up, the spin here is S1 plus S2, which commutes with E12 spin. Anyway, this is a set of commuting operators. Now, I'm going to tell you without going into too much detail that in the case of helium, we can sort of ignore parity. It's because it doesn't produce anything interesting if we carry it on. So I'm just going to drop it here and ignore it. In a sense, the reason it doesn't is because it turns out parity is a function of L for the cases that we're interested in. That's why we can drop it. If we do L, we don't need to worry about parity. This might not be a surprise because that's what happens in hydrogen. Remember, the parity is a function of L. The parity is -1 to the L. In any case, for helium, we can ignore parity. Parity is more important in multi-electron atoms. So let's work with this collection of commuting symmetry operators that also commute with the Hamiltonian. Let me write down the notation for the eigenvalues of these operators. We'll use a lowercase e for the exchange operators, E12 spin, total E12. Then I'll use L and M sub L for L squared and LZ, and I'll use capital S and capital M sub S for S squared and S sub Z. Let's let these be the quantum numbers here. Quantum numbers. Let's see, is this still on the page? Yes, I think so. So these are the quantum numbers of operators that commute with the Hamiltonian and with each other. So we know that the Hamiltonian can be simultaneously diagonalized with all these operators, or to say it another way, if we go to the subspace of the Hilbert space, which is a simultaneous eigenspace of this collection of symmetry operators, then, or break the Hilbert space up into subspaces, which are these eigenspaces, then we know the Hamiltonian does not connect those different subspaces. In effect, it can be diagonalized on each subspace separately. Now, inside one of the subspaces, we can sequence the energy levels like so by some index number n. Let's call n a sequence number. It starts with some beginning, might be 1, n equals 2, and so on like this. These are the energy levels inside one of these eigenspaces. And as a result, the energy eigenvalues can be characterized by these set of 1, 2, 3, 7 quantum numbers, as well as the sequencing number n. Energy eigenstates can be that we can do that. We know this without looking at anything about the Hamiltonian except its symmetries. Now, however, these quantum numbers are not independent of one another. Some of them are superfluous. Certainly the E12 is superfluous because for the physical states anyway, that's -1. That's by the symmetrization postulate. That requires the orbital and spin quantum numbers to be opposite one another. So if we know one of them, then the other one is determined. Moreover, as we've seen, if we know the spin quantum number, that's to say the quantum number of the operator S squared, then that determines the E12 spin and therefore E12 orbital. So knowing S, the S quantum number means that these two are superfluous as well. All three of the exchange operators in effect quantum numbers become superfluous. By the way, something I forgot to mention was that in writing down these quantum numbers, capital L, ML, S, and MS, I'm using a convention which I'm going to follow for the rest of this course, which is to use capital letters for the quantum numbers of an entire atom or other larger system, and reserve lowercase numbers, characters for the quantum numbers of individual electrons. I think it's a useful distinction. All right, in any case, this is the rule I'm following here. So the result is that the energy eigenstates are characterized by sequencing numbers inside the symmetry class. And the symmetry class is determined by L and S and ML and MS. So we can write a ket with those quantum numbers like that. And we know then that those quantum numbers uniquely identify an energy eigenstate without doing any further work. Actually, there is a worry. Maybe, how do we know there's not degeneracies inside a symmetry class? The reason is that once we've taken care of the symmetries, degeneracies are very unlikely. So in fact, they really don't happen. So a single sequencing number 1, 2, 3 like this. N doesn't have to start with 1. You can start with something else, but some sequencing number, these quantum numbers suffice for identifying energy eigenstates. So the Hamiltonian acts on this, then is going to bring out an energy. Now, what quantum numbers does the energy depend on? Well, we know what it doesn't depend on. It doesn't depend on the magnetic quantum numbers, because the Hamiltonian is rotationally invariant under both spin and orbital rotations independently. And as a result, it's a scalar operator with respect to both of those operations, both those types of rotations. And basically, it's a consequence of the Wigner-Eckhart theorem that the Hamiltonian, that the energy levels are independent of the magnetic quantum number. And so the energy can only depend on the NL and S. So let's write that, E sub NLS, multiplying the same state, NLS, ML, and MS. And that means that the energy eigenstates then, which are given here, the energy eigenvalues, that they're degenerate by 2L plus 1 times 2S plus 1, which is the number of possible combinations of the two magnetic quantum numbers. This is then the order of the degeneracy of those energy levels. So all of this comes out from a straightforward analysis of symmetries. Okay. Now, given the fact that the Hamiltonian, which I'll bring it back again, here it is a purely spatial operator, you might think that the energy eigenvalues should not depend on the spin quantum number. It's a logical thing to think, but actually they do. And this is characteristic of multi-electron systems. And the reason is the following. It has to do with the symmetrization postulate. If there were no symmetrization postulate, it would be true that the energies would not depend on the spin quantum number, because a Hamiltonian doesn't involve the spin. However, in that case, the energy levels would depend on the orbital exchange. And the reason is that if you have two two states that differ by orbital exchange, the orbital exchange gives you you're symmetrizing or anti-symmetrizing a wave function to get states of opposite orbital exchange. These states are going to have rather different distributions of probability in three-dimensional space, and therefore different Coulomb energies. Just by Coulomb's law, that it's unlikely the energies will be the same. And so the energies would depend on E12 orbital. In fact, they do depend on E12 orbital even in real helium. It's just that we don't write down E12 orbital because it depends on E12 spin, which in turn depends on S, because of the symmetrization postulate. So in other words, in real helium, the spin quantum number determines the spin symmetry, which determines the spatial symmetry, which determines the distribution of the wave function in three-dimensional space, which determines the charge cloud, which determines the energy, Coulomb energies. So not only does the energy depend on the S quantum number, the energies are large, i.e. they are Coulomb energies. They're not energies that are characteristic of spin dynamics, such as magnetic dipole interactions. Those things are actually there. We neglected them in the Hamiltonian, but they're present, but they're very small compared to Coulomb energies. And so what we find then is, as a consequence of the symmetrization postulate, the energies do depend on the spin state, and they do so in a large manner, much larger than would be expected by magnetic energies. This energy is not a magnetic energy, it's a Coulomb energy. So this occurs in helium. It also occurs in ferromagnets. In fact, it's the basic explanation of the energy scale in ferromagnets. Prior to the advent of modern quantum mechanics, that means in the years of the 19-teens, physicists realized that the energy that's involved in magnetizing and demagnetizing ferromagnets, which means flipping the spins up and down, arrays of spins, that those energies are much less than they're much greater than the energies of the interactions between the magnetic dipoles. And one can tell what the magnet of the dipole is. It's roughly a Bohr magneton. And so it was a mystery, the energy scale. Why the large energies in ferromagnets? Well, the answer was given by Heisenberg once he understood the the symmetrization postulate is an outcome of his work on helium in 1927. I think he did it very early in quantum mechanics. First theory of ferromagnetism. The basic idea is that when the spins are aligned, it means that the spin part of the wave function is highly symmetric, and it means that the spatial part of the wave function is therefore highly antisymmetric. This keeps the charge clouds far apart and reduces the Coulomb energy. So that explains this that's the basic mechanism for ferromagnets. So this is a simpler version of this in the case of helium because we have only 2 electrons, but it's the same idea and it's the same mechanism. All right, so the energies do depend on the spin quantum number. All right. Now, there's a question about spectroscopic notation for these levels, E, N, L, S. I'll tell you about it. The spectroscopic notation is this, is we write it like this. We have to have spectroscopic notation in order to give you some rules that are just for memorization. You know, my wife is a doc, so she has to deal with prescriptions. Well, the drug companies invent random computers that the drug companies own, invent random names, you know, Molexilab or something like this, that have no relation to anything. They have no logic. They're not connected with the chemical formula for the drug, nothing. So if you're a doc, you have to memorize all these utterly just wasted brain cells, memorizing these wasted, stupid names. Anyway, so we have a little bit of that in atomic notation. The ENLS, the spectroscopic notation is N, 2s plus 1 as a superscript, and then the L, the orbital angular momentum, where the orbital angular momentum is replaced by the code letters S, P, D, F, and so on that we've seen before, that correspond to L equals 0, 1, 2, 3, and so on like this, but with capital letters because they're the quantum numbers of the whole atom and not of individual electrons. So, for example, the state 2 triplet P would be read this way, 2 triplet P. What this means is that N equals 2, that's the 2 here. The S is equal to 1, that's the triplet part. That's 2S plus 1 is 3. And the angular momentum L is equal to 1, that's the P code number for L equals 1. That's the translation from the code into the quantum numbers. Okay, that's the notation for the levels of helium. All right. Now then, okay, so we've done a lot in understanding the levels of helium without ever really touching the functional form of the Hamiltonian, except for this to notice that it's purely spatial and rotationally invariant. We need to get our hands dirty with the real content of that Hamiltonian. I'd like to begin this by presenting some experimental facts, namely involving ionization potentials. So the ionization potential of an atom, first ionization potential, is the energy required to remove 1 electron and take it out to infinity. If we do this with helium, we take a helium atom and we remove 1 electron, what's left behind is a helium plus ion, and then there's an electron, and the energy that's required to do this is minus 0.904 atomic units. I'll be working, did I say this? We'll work in atomic units, E equals H bar equals M equals 1. So this is 2.904, 0.904 atomic units. The ionization potential for hydrogen is only 1/2 of an atomic unit. That's the equivalent to the 13.6 electron volts, which you certainly memorized. And you can see this is larger than hydrogen. In fact, helium has the highest ionization potential of any atom in the periodic table. It's the most difficult to ionize. Once you remove 1 electron, you can remove another one. Then there's a second ionization potential. If we do that with helium, we get helium plus goes into helium plus plus, doubly ionized, plus a second electron, which is removed. And this takes 2.0 atomic units of energy to do that. So what this means is that to remove both electrons and to take them out to infinite separation requires a total of the sum of these 2 energies, which is 2.904 atomic units of energies to completely ionize helium. Now, in non-relativistic mechanics, the point on the energy axis that we call E equals 0 is really a matter of convention. it's like the ground of a circuit. You get to choose conventionally what's going to be the ground, and then everything's measured relative to that. There's an exception to this in general relativity where absolute energies are important, but for our purposes, we can say that it's only relative energies that are physically meaningful, energy differences. In the case of electrostatics, think about a course like 110, a bunch of charged particles. It's fairly common to regard the state of zero potential energy to be one in which all the particles are removed to infinity at an infinite distance from one another, separated by infinite separation. Well, that's just what we've done by the double ionization of helium. The nucleus and the two electrons are separated at infinite distance. So if we follow that convention and call that the 0 point of energy, then you can see that the original helium atom we started with is at an energy of minus 2.904 atomic units compared to that reference. So we call that reference the 0 of energy, then this then becomes the ground state energy of helium. So this is in fact E0 is equal to that with this convention. By the way, the Hamiltonian that I wrote down, let's go back to it here. Here it is. The potential energies that we're using here are following that same convention, because when R1 and R2 and R12 all go to infinity, the potential energy goes to 0. This is just Coulomb energy, but we just set it up so it's 0 when all the particles are at infinite separation. So let's use that convention, and if we do, then this is the ground state energy of the helium atom. Let's do the same thing for the hydrogen H- ion. It's interesting to compare helium with H- as a contrast between two cases. So if we take H- and ionize it once, we get neutral hydrogen plus a free electron. And this requires, the binding energy is rather small. It's minus 0.028, like this. Then if we take neutral hydrogen and rip off one more electron, of course we get H+, which is a proton, and then a single electron, and this requires 0.5 atomic units. This 0.5 atomic units is, of course, the ionization potential of hydrogen. That's just the usual 13.6 electron volts, again, written in atomic units. The second ionization potential, 2 for helium and 0.5 for H-, is easy to understand because helium plus and neutral H are both of them hydrogen-like ions. So removing the last electron, we know the theory that we know what the formula is. The energy is Z squared over 2, or the ground state energy of a hydrogen-like atom is minus Z squared over 2. That's what this 2 is. It's minus 2 squared over 2 is minus 2. Here it's minus 1 squared over 2 is minus a half. So these ionization potentials were easy, the last one. However, the ionization potentials for the first electron is much harder, much more difficult to calculate. If you like, these are experimental values that I'm giving you here. All right. In any case, this is the data on the ionization potentials for both helium and H-. I've taken some diagrams out of the notes and I enlarged them so that I can put them on the page here. Let me do that because it says because they're drawn better than I can draw by hand. Here's the diagram for helium. Let me explain this diagram. This is just based on the ionization potentials. So here's the energy of 0, which, as I just explained, is given when the helium atom is totally ionized and all particles are moved to infinity. Here's the ground state energy at minus 2.904. When we remove the first electron, first ionization, we jumped up by 0.904 up to an energy of minus 2. And it was the second electron moved us all the way up to an energy of 0. Now, the reason that this is marked and shaded up here and is labeled with a continuum is because after we've removed the first electron and taken it out to infinity, visualize the helium ion left behind and a million miles away is the electron. That electron, you might as well make it stationary without any kinetic energy. If you want to give it kinetic energy, you can do so. And since it's at infinite separation, you can make the kinetic energy anything you want continuously. There's no quantization of it. So in other words, above this state here, but in energy above this state, by giving kinetic energy to the electron, you have a continuous spectrum. The quantum spectrum becomes continuous at minus 2. So that's why this is labeled continuum. The continuum begins in an energy of minus 2. This is different from what we had in hydrogen, where the continuum began at energy 0. So I'm pointing this out now. This is what happens in the multi-electron atom. Continuum begins basically at the ionization potential of the first electron, following the conventions we're using. If we do this for the H minus ion, I've got a similar diagram here, but the energy scale's been scaled by a factor of 4. As you can see, this is -1 for helium, and this is -1/4 for hydrogen. That's because of the z² factor that enters here. And the energy of the ground state of the H minus ion is -0.52. It's only slightly below the ground state energy of hydrogen itself. You see, the binding energy is rather small. So if you compare these two, you can see that this is much more weakly bound, relatively speaking, than the case of helium, the second electron. All right, so that's the some of the data that comes from ionization potentials. All right.
I have a question that might just come from me slightly misunderstanding the pictures you just showed, but
Yeah, I'm gonna bring the picture back here. Let's do it for helium. Here it is. Yes. What's your question?
Wouldn't it be possible for using both the helium ion and the electron to get our energy, to give the electron just enough kinetic energy that it gives a net energy of 0 without having the second ionization?
No, because we're defining the condition of the state of 0 energy to be one in which all 3 charged particles are at infinite separation. Now that's just a convention, but it's a common one in electrostatics, and it's in accordance with the potential energy that we wrote down in that Hamiltonian. So the situation you described is one where I think what you're thinking is you've got these 2 electrons in orbit, and you're going to kick one to give it enough kinetic energy that it can escape, right?
Mm-hmm.
Well,
Yeah.
if you gave it just enough kinetic energy to escape, to go to infinity, and you waited a long time, so it went a long way away, essentially its kinetic energy goes to 0. Then the state that you're in is this one right here. You have a helium plus ion left behind and 1 electron at infinity with 0 kinetic energy.
So why does the kinetic energy have to go to 0 at infinity?
It doesn't, but if you kicked it with a kinetic energy, to give it kinetic, if you kicked it with, I'm sorry, it's already got kinetic energy. If you kicked it with, to give it enough extra energy of 0.904, that would give it enough energy that it would escape and move to infinity.
Mm-hmm.
It would go on a hyperbolic orbit, basically. You know, that's in solar system language. It would be a comet that would escape, but in such a way that it asymptotes to 0 velocities and moves out to infinity. Does that help? Okay, because you still left behind that other electron. You see.
Okay, so that's the one that you could
That's
give you the
one
continuum.
that's responsible
Okay.
for -2 here. This extra -2.
Okay.
All right. All
Thank
right.
you.
And by the way, it takes more energy to remove the second electron, because when we remove the first electron, the nuclear charge was screened by the electron remaining behind. So for most of the distance that it's pulling away, it only sees a positive charge of +1 behind it, not a charge of +2. The second electron sees the full charge of +2. That's why it takes more energy to get it out. Okay. Now, what this diagram makes clear is that the bound states of the helium atom lie between the ground state energy at -2.904 and the ionization threshold, which is at -2. So if we want to study the bound states, we only need to look at that energy interval from between -2 and -2.904. So what I want to do now is to draw you an energy diagram for what the energy levels look like in that range. So let's put this over here. So it looks like this. Let me draw a horizontal axis here. And this is going to be the continuum threshold. So this is E equals -2. I don't know if you can see that, but that's equals -2. I want to make a plot of the energy levels of the various states that are concerned. And so let me divide this into a right and a left half, like so. And what we'll do is we'll put the para states on one side, which are, of course, are spin 0 singlet states, and we'll put the ortho states, which are spin triplet, on the other side, s equals 1. So that takes care of the spin quantum numbers. We know the energy eigenstates have spin quantum numbers. This takes care of the spin quantum numbers. They also have L quantum numbers. Remember the n if you recall, the The energy eigenstates were characterized by the quantum numbers N, L, and S, remember? The energy levels.
Could you bring the paper down slightly?
Like that, yes.
Yeah, thank you.
All right, so we also need an L quantum number. So let me fill that in. Let's put in S, P, D like this on this side, and let's put in S, P, D on that side. This goes all the way out, S, P, D, F, and so on. The L goes all the way out to infinity. I've just listed the first three here. We, in effect, have 6 columns now, giving us the values of L and S quantum numbers. Now, the ground state is actually a singlet S state, and it's down here at, let me write it down here. This is at an energy of minus 2.904. And the quantum numbers of this state are that it's one singlet S. It's the lowest level in the singlet S column. Singlet because you're in the singlet side, and the S because you're in the S column. Anyway, that's where it is. That's where the ground state is. Somewhere up above here is a 2 singlet S. Somewhere up above that is a 3 singlet S. And so on. This goes on up, and there's an infinite number that accumulate like this. You see the n quantum numbers, just the sequencing number is increasing like that. Now then up here is in the P column, there's a 2 singlet P. And there's a 3 singlet P up here. And this goes on up, there's an infinite number that going up like this. And then likewise over here, there's a 3 singlet D. And this goes on up like this. I'm going to mainly concentrate on the n equals 1 and n equals 2 levels, but this is what they look like on the para or singlet side. Now on the ortho or triplet side, it looks like this. I want to draw this as I can. You've got a level here, which is a 2 triplet S. And up above here is a 2 triplet P. And then there's a 3 triplet S and so on. And these things continue up like this and give you accumulations of levels up like that. These levels that occur on these two sides, well, all right, anyway, this is what the actual spectrum of helium looks like. If you like, I'm giving you the experimental data. That's one way of thinking about this presentation of this page here. It's a little bit of a lie because the experimental data is not energy levels. Experimentally, what you get are differences between energy levels. You get the frequencies of photons. So you have to disentangle that data in order to find out what the energy levels are. And then I'm also assigning quantum numbers to them, which requires some theoretical knowledge. So this is actually a little more than experimental data. But in any case, let's just take this. I'm giving you the answer. This is what the helium spectrum looks like. Let's try to understand it, understand some features of it. If I just looked at the singlet side, the spectrum is not that different from hydrogen, except that in hydrogen, the P and the S levels would be degenerate. But you'll recall that in alkali atoms like sodium, the higher angular momentum levels have a higher energy. Sometimes I call this the staircase effect, meaning that the levels go up as a staircase as angular momentum increases. And so thinking of something like lithium or sodium, the alkali metals, this side of this is pretty similar. If we compare this to the triplet side, the ortho side, the main thing that we see is that there's nothing corresponding to the ground state. That's to say, there's nothing over here. If it were here, it would be a 1 triplet S. But it's missing, so I'll put a question mark here. Why is there no 1 triplet S state? In fact, allow me to make a set of observations about this spectrum. The first one is that there is no 1 triplet S state. Okay. You might object to this. You might say, oh, this was just your numbering convention. Why didn't I just number this one? Instead of starting with 2, why didn't I start that with 1? And that would be a 1 triplet S, right? The reason I don't number this with a 1 is because it's clear and confirmed by theory that these two n equals 2 levels, this S and P on one side and the S and the P on the other side, are related to each other. I mean, they're actually connected. It's logical to call this an n equals 2 level. Plus, there's a substantial gap, which probably is more exaggerated than my diagram indicates, between the 1 levels and the 2 levels. There's quite a bit of space in there. All right. In any case, there is no one triplet S. Here's another feature that we can observe. It's what I call the staircase effect, as I explained a minute ago. It means that if I hold, let's hold S fixed, the spin fixed, then the energy increases as L increases. And this is what I call staircase. The third thing to notice is that if we compare the singlet and triplet sides, and I intended to draw it this way, is that these triplet states for this otherwise the same quantum numbers are actually lower in energy than the corresponding singlet state. So what that means is that if L is fixed, then the energy decreases as the spin increases. Spin can only go from 0 to 1. So energies go down if you do this. All right. So these are 3 qualitative features of the helium spectrum, which not tonight, but at some point we will obtain insight into this by means of perturbation theory. All right. Okay, so that's the helium spectrum. That's the basics of it. All right.
Sorry, I think I'm a little confused by the spectrum. So if we look at the, I'm trying to go through my notes. So if we look at the parasite, that's the S equals 0 state, then we should, because it's a parastate, then we should only have spatially symmetric wave functions. So we should have, so how do we have P states in there? 'Cause doesn't it have a,
yes, because this is the eigenstate of a 2-electron atom, and the P is a quantum number of total L squared, which is L1 plus L2. So that, by the way, thank you. That's a very good question. Because in hydrogen, okay, so there's different aspects of this question. In hydrogen, the parity of the state is determined by the L quantum number. We know it's -1 to the L. However, this is helium, and we're talking about exchange symmetry and not parity. So that's the first part of it, is that it's not the same operator. But the second part of it is that even if you want to talk about parity, you now have 2 electrons. It's not just a single electron system. So the parity involves the wave function of both electrons. But the simplest way to answer your question is that this isn't parity, this is exchange.
okay, I think that makes sense.
All right, but now to confuse the matter even further, in the case of the hydrogen molecule, I pointed out that the exchange quantum number was -1 to the L. At least the spatial part of it is. A spatial exchange is -1 to the L. And that's because in the diatomic molecule, when we go through the center of mass transformation, we find that the exchange operator flips the sign of the relative position vector. And that's the same thing that parity does to it. So the rule for parity and the rule for spatial, not total exchange, just spatial exchange, is the same for diatomic molecules. It causes massive confusion, by the way. Don't confuse exchange with parity. But in helium, these are not central force wave functions. These are 2 electrons now orbiting around a central nucleus. And there's no relationship between parity and exchange here. I'm glad you pointed that out, though, because that's something to keep in mind with this. Okay.
A question.
Yeah.
So you just drew the point spectrum below -2, and then said it's continuous spectrum above there. But can't there be point spectrum embedded in the continuous spectrum?
Yeah, I'll get to that. There is, okay. But they aren't real eigenstates. They're only approximations. Yeah, I won't get it to you tonight because I'm out of time. Okay, so this is a place to stop. If you want to read ahead, take a look at the part in the notes about the doubly excited states, and you'll find out about that. I'll cover it in the next lecture. Okay, so that's all. Are there any other questions tonight?
I have a question. Oh.
Go ahead. Go ahead.
Okay, thanks. I think actually as to it's similar to what was just asked. I think about like where the bound states can be found. So did you just say that there are bound states found in the continuum like area?
Yeah,
Or
so I don't have time to go into it tonight, but there are what you call discrete states embedded in the continuum, but only in an approximation to helium, not in real helium.
okay, cool. Yeah, that was just my question. I just didn't understand how there would only be bound
Right,
states. with that
right.
sort of- but
Those
okay,
things are actually quite interesting.
okay, thank you.
Yeah, there was another question.
Yeah, it was just a little more logistical. Are we to expect to do homework this upcoming week?
You mean like due tomorrow?
No, I mean do next, I guess, Friday.
There'll be a homework they'll be due next Friday.
Okay, got it. Thank you.
Yeah, so so this will be like last semester. I give out a homework at the end of a week's worth of lectures that covers that week of lecture. So that's why there'll be a homework coming out tomorrow to cover these last two lectures. And it is due 1 week later. There's a policy about late homeworks. If you haven't seen it before, read the logistic information that's on the website, and that'll fill you in. If you have any questions about it, feel free to ask me about it.
All right, gotcha. Thank you.
All right. Any other questions? All right. If there's no other questions, I shall stop screen share. And then I shall stop recording.